Hello students, once again we will resume chapter number 10, light, reflection and refraction. And right now we'll discuss about the topic of refraction through a rectangular glass slab. As you can see on the board, we have a rectangular glass slab that is A, B, C, D. Okay, so now here above the glass slab we have rarer medium. The medium of glass is denser comparative to the air, and again over here it's a rarer medium. Now in absence of this glass slab, suppose I incident a ray. It will travel on a path P to O, O to Q prime. The path would be like this, but when I insert the slab in its path, now it will travel from P to O, O to O prime, and from O prime to Q. Now here you can see that because of the change in medium twice a time, the refraction takes place twice a time. Okay. At this point O, the first refraction takes place. And at point O prime, second refraction takes place. Once again, see, PO is an incident ray. Now O prime is an refracted ray. And from O prime to Q, that is emergent ray. Now, as we know that this is normal, over here also we have drawn a normal to the surfaces. At point O, first refraction takes place. So we got two pairs of angles. One is I1, that is called angle of incidence, and R1, that is angle of refraction. Over here also, once again, we get two pairs, that is I2 and R2. I1, similar to I1, I2 is angle of incidence, R2 is angle of refraction. But here R2 is also called angle of emergence or emergent angle. Now this particular question is very important as it can be asked in 3 mark or 4 mark.
Students, now moving on to the next topic, that is laws of refraction. The first law is the incident ray, the refracted ray, and the normal drawn at a point of incidence, they all lie in the same plane. Another one is for a given color and for a given pair of media, the ratio of sine of angle of incidence to the sine of angle of refraction is always constant. Now this appears as similar to the laws of refraction, but you see the second point is different. Okay. Now, as we have learned this thing, then comes the topic that is refractive index. But before starting this refractive index, I have a question. The question is written over here that why refraction takes place when a light travels from one medium to another. Now, if you guess the answer right, I would appreciate that. The answer to this is that is speed of light varies from a medium to medium, but it is the maximum speed in the vacuum, then a bit lesser in air, and it decreases further in different transparent media. Okay, so from that topic we get this thing that is refractive index of a material. Now as you can see in the diagram, this is the surface which separates medium 1 and medium 2. Just assume that medium 1 is air and medium 2 is glass. This is my incident ray, this is my refracted ray, I is my angle of incidence, and R is angle of refraction. Now, suppose I want to know what is the refractive index of medium 2 with respect to medium 1. That is given as velocity of light in medium 1 to the velocity of light in medium 2. That means this ratio of velocities will give me the refractive index of 2 with reference to medium 1. So this is refractive index. Okay. Or we can also say that refractive index of medium 1 with respect to medium 2 is given as ratio of speed of light in medium 2 to the speed of light in medium 1. But this, what I taught you, is also known as relative refractive index. But what if I want to know what is absolute refractive index? Then we have to go for the ratio, that is absolute refractive index of any medium is defined as the ratio of speed of light in vacuum to the speed of light in the medium. This ratio gives you absolute refractive index. And remember, there is like ever it is not possible to have refractive index below 1 because the speed of light is always maximum. Okay? And that means it is greater than the speed of light in the medium. That's right. Now here the speed of light which we have to memorize as 3 × 10 to the power 8 meter per second. That is the vacuum. And all other speeds which we'll get for different medium, that will be lesser than this value. That is going to substitute over here. So this is about laws of refraction, refractive index, and absolute refractive index. There is a bit of confusion for the kids that is between optical density and mass density. Now let us make it clear that optical density has nothing to do with mass density. See, optical density is defined as the ratio of speed of light in vacuum to the speed of light in medium. Whereas mass density, which is indicated by rho, that is defined as the ratio of mass by volume. So they are totally different and they do not interfere in each other. Now let us have a little example, that is the example of kerosene and water. Now all of us knows that from the point of view of mass density, kerosene is lighter compared to water. But if I talk about the optical property of kerosene, that is optical density, then optical density of kerosene is greater than the optical density of water. So eta k is greater than eta of water, whereas rho k is less than rho of water. Got it? Okay. So the next topic is refraction by spherical lenses. As you can see, I've given you the diagrams of two lenses which is there on our syllabus. That is, one is convex lens and another one is concave lens. See, in this kind of a lens, the edges are thinner whereas the center portion is thicker. That is what we term as convex lens, or it is two spherical surfaces, so it is also called double convex lens. Now here you can see that the edges have broader surface area compared to the center section. These kind of lenses are known as concave lens or double concave lens. Now, it is made from a sphere, so the center of that sphere will be once again called as center of curvature, which is, now here there are two curved surfaces, so we will indicate it by C1 and C2. Similarly, over here also center of curvature is C1 and C2. Now, when we take about the topic of rays, but before that, again, the line joining the two center of curvatures, that is called principal axis. Here also, from C1 to C2, that is principal axis. Now here, the central portion of the lenses is indicated by O, and that is optical center. Okay. Now, the other one, when the two rays are incident parallel to principal axis, after undergoing refraction from the lens, they meet at a particular point. That point is termed as focus or principal focus. Here, we can see that the two rays which are parallel to the principal axis are diverged together. So when we extend back in the same direction, we get a point where the meet, that is called principal focus. So here they appear to meet, and here they actually meet. They are termed, these points are termed as focal points. Again, if the scenario would be from this side, then focus would be that side. So we will have two focus. Now, one is F1 and F2. Here also F1 and F2. So we got three things: center of curvature, optical center, principal axis, principal focus. The distance is called focal length, that we know it. The distance from optical center to C2, that is what we call it as radius of curvature. Now here we can see that the effective radius, or we can say diameter of this, if I consider from A to A prime, that is the diameter of the lens, that is called aperture of the lens. During the explanation of rest of the chapter, I'll consider that my aperture of the lenses is very small compared to the radius of curvature. Okay, so syllabus is confined to that particular exhibition. Okay. Now, as you can see over here, I've written some names. Now here, the rays converge to a point. So it is also given a name, that is called converging lens. In common terms, if you use this lens, you see that the fonts, if you are reading a book and you're using the convex lens, the fonts appears larger in size. So commonly it is also called magnifying lens. And a very famous experiment, which is very common, you can say, that you place it, you focus the focal of the lens over a paper in front of a sun. Okay, you see that the image of the sun is formed on the paper, and within a while, paper starts burning. Right, because the rays are concentrated at a particular point. Okay. In the case of a concave lens, you can see that the rays are diverged after refraction. So it is given a name that is called diverging lens. Okay. Now, I've used the word double concave and double convex. The reason is over this slide. As you can see, I can also make a lens which is having only one surface made out of a spherical surface. So, such a lens is called plano-convex. If it is made like this, it is called plano-concave. There are also various types, like we can have meniscus lenses and all, but that is not included in this lens. Okay, so this much will keep it for instant. Moving on to the next topic, that is image emission by lenses using ray diagrams. We have three steps on that. Okay, so number one, if the ray is incident parallel to principal axis. For the concave lens, for the convex lens, after refraction, the ray will pass through principal focus. And in the case of concave lens, the parallel ray will diverge away, but if you extend it backward, it will pass through principal focus. Side 2. See, if the ray is incident in such a way that it is passing from principal focus or it is appearing to pass through principal focus, then after refraction, it will be parallel to principal axis. And the third one, that is, if the ray is incident in such a way that it passes to the optical center, irrespective of whether it is a convex lens or a concave lens, no issue with that. But if a ray is incident in such a way that it passes from optical center, it will undergo zero deviation. That means it will just pass through it. Okay?
So kids, moving on to the topic, that is image formation by convex lenses and ray diagram of it. In this, the first case is if the object is at infinity, its image would be formed on the other side of the lens at the principal focus. This image will be real and inverted, but it will be of point size. We can call it highly diminished. Case 2. If the object is placed beyond 2f, its image will be formed on the other side of the lens between f2 and 2f2. The size will be diminished. It will be real and inverted. Talking about the third case, if the object is placed at 2f, its image will also be formed at 2f but on the other side of the lens. The size will be similar. That means the size of object is equal to size of image. It will be real and inverted. Talking about this case, if the object is placed between 2f and f, its image will be formed on the other side beyond 2f. It will be magnified and it will be real and inverted. Then comes this point. If the object is placed at the principal focus, its image will be formed at infinity on the other side of the lens. The image will be highly magnified, real and inverted. Now comes this particular case, which is justifying its name, that is magnifying lens. See, if the object is placed between optical center and principal focus, okay, so its image is formed on the same side of the object. That will be magnified, but now this time it will be virtual and erect. So this is what we use it in our day-to-day life. When we place it in front of a newspaper, we can magnify the digits of that or words of that. Thank you. Image formation by concave lens and ray diagram. Now in this particular case of lens, we only have two cases. If the object is at infinity, its image will be formed at principal focus. Now as it is formed on the same side, it is virtual and erect but highly diminished. Here, if the object is placed beyond focal, right, its image will be formed between focus and optical center on the same side. So this image will also be virtual and erect. Okay. Now, as you can see over here, that it is diminished in size. Now, you can take this object anywhere, you will get the same result of the image. It will be always forming between F1 and O. So, these were two cases of concave lens. Moving on to the sign conventions for the lenses. Now, the first is, it is somewhat same as spherical mirror, but here you have to think that is the distances are to be taken from optical center along the principal axis or parallel to principal axis. Then convention is same. This side will be negative, this side will be positive, upward positive, downward negative. Along with that, we have two more things in this. That focal length of a convex lens is always taken positive, and focal length of a concave lens is always taken negative. Now, after that, we'll move to the mathematical topic of the lenses, that is lens formula. Now here it is, inverse of image distance minus inverse of object distance is equals to 1 by f. This formula correlates three things: image distance, object distance, and focal length of the lens. This is called lens formula. In numericals, this will be very handy. Then it falls for the magnification. Now by magnification, you can identify whether the object is magnified, means it is enlarged, or it is diminished. Now the ratio of the height of image upon height of object will give you magnification. But in the second formula, there is a bit of change, that is the ratio of image distance to the object distance is your magnification, unlike the case of the mirror. But the lens, there is no negative sign over here, but in mirror we had a negative sign. So remember, magnification for the lens is positive V by U. See, as for the sign convention, you may have to take V negative and U negative, but in the formula of magnification, negative sign does not appear. Moving on to the last topic of the chapter, that is power of lenses. Power of lenses is defined as the capacity of a lens to diverge or converge the rays which is incident over it. If I talk in the terms of mathematical formulation, then the power is given as the ratio 1 by f, right? That means inverse of focal length is power. Now here you have to take the unit of focal length in meters. So the power unit will become meter inverse, or in the terms of SI, it is a unit that is called diopter, which is symbolized by capital D. Now remember, as we know that the focal length of a convex lens is positive, so its power will also be positive. But if I go for a concave lens, its focal length is negative, so its power will also be negative. So now let us take a small numerical over here, that if you prescribe some lenses at an old age and your power is given to you, that is plus 2D, that is plus 2 diopter. That means your focal length can be calculated as 1 by P, that is 1 by 2, and that will come out to be 0.5 meters. But I want it in centimeters. I'll multiply by 100 and I'll get it 50 centimeters. So the focal length which you need to wear on of a lens, that is about 50 centimeters. I hope you enjoyed this chapter. If you have any queries, get back to us on the same.